Okay, hello everyone, and welcome to this lunch event focusing on event sourcing. First of all, I must inform you that this event is being recorded and it will be available later on YouTube or some similar platform. So we, Swenug Stockholm and Swenug Örebro and Infozone together are really glad to present to you Alexey Zimarev and Greg Young. They are both very well known when it comes to software development, patterns and practices, and especially event sourcing. They will be covering more or less the whole spectrum from using event sourcing in production down to the underlying software storing the actual events. Alexey will go first, followed by a Q&A. Greg is on after that, starting at 1 o'clock. But before handing over the mic to Alexey, here is Andreas Hagsten and some short information about today's host.
Yeah, thank you, Fredrik. We have two great speakers with us today, and 104 attendees at the moment, but it's over 230 registered. So that's a big wow and a big welcome to all of you. My name is Andreas Hagsten, and I'm the business area manager for system development at Infozone Sweden. I know you're eager to get started, but I just want to say a few words about Infozone and why we're hosting today's event. So Infozone was founded in 2007. We are an IT consultancy firm focusing on the system development, business intelligence, and virtual infrastructure. We have 5 offices globally. 3 of them are in Sweden, where we have Stockholm, Örebro, and Lund. And in the US, we have offices in Chicago and New Jersey. So why are we at Infozone doing this? Why are we having this event? Well, first of all, we love these kind of talks. So we're doing it because it's fun, right? And we believe that we in the developer community can share knowledge with each other and learn from each other, and that we can share our knowledge with other developers. I mean, that's what we are really doing here today, right? We have 2 great speakers sharing their knowledge and expertise to all of us, and that's a great thing. And we also want to give back to the meetup community. So myself and many of my colleagues have attended meetups over the years, and this is a good chance for us to contribute back to the meetup community. And I don't have anything else to say really, except that I hope you will have 2 great hours. And one last thing, you can feel free to ask questions in the chat. And I would like to ask you to keep your microphones off during the event, unless Alexey and Greg says otherwise. Thank you. And Alexey, if you're ready, it's all yours.
Yeah, let me share. All right. See my screen?
Yeah.
All right. I'm here today to talk about event sourcing in production because my main focus, as I see it at the moment, is to, I build event sourcing systems for a living and advise people how to do it. So it's kind of what I do, right? And during several years since I first met Greg back in, I don't remember when it was, on the course of the advanced event sourcing and like applying DDD and stuff back in London, an old building of Skills Matter, which luckily exists still. So the stuff that I was building and people that some of my colleagues are here who were participated in this success projects and failure projects, they know some of the stuff that I'm going to talk about. So I want to talk about pains and gains, and because I sometimes call this, it's not the same talk, I just prepared the slides. But overall, on my workshops and when talking to people, we discuss things that happen when you are building, right? And we see that at some, like, or we forget about at some point we put systems to production, and then there is another layer of pain and maybe another level of gain that you get when running event source system in production, but we already touched this. So I'd like to cover some of the lessons learned, and hopefully I can give you some advice about mitigating those issues that we experienced. And maybe even like don't see issue as an issue, but see as an opportunity to improve your design, to improve your system and its performance. So just go through the stuff that I remembered yesterday and today, and I think that these are important points. So if you ever like followed me on Twitter, you've probably seen that about a few weeks ago I started a big Twitter storm about posting diagrams that I see, or at least my opinion is that event sourcing is not done in the right way. And this is one of the diagrams, and you can see from the source where it comes from, and that's a big kind of challenge for us in the event store to explain how to do event sourcing in the right way when we have such big players saying how to do it not right way. At least that's what I think. So a lot of people do event sourcing, or they think they do event sourcing, but in fact they do something similar to event-driven architecture. On this diagram, you can see that application, what they call right interface, whatever, they put events to the store, and events represent the state transitions. That's basically the essence of event sourcing, right? And somehow through some sort of event handler, they put it in the application state. So in this picture, you can clearly see that event store and event queue and events in general are not seen as application state at all. It's some other database that's been populated from events, and this is what the users see, which is okay. That's CQRS, right? And the point is, as soon as the application state is used for decision making, so this particular one, then comes trouble. So we have a delayed state. There are two parts of the command handling. So first of all, when your user, for example, looks at the screen, that's what comes from the read model. This comes from a reporting model. Not necessarily, but most of the time. And this is what you see on the screen. And then you make some decision. For example, you want to book a room, you want to pay someone and stuff like that. When this command comes to the system needs to make a decision on a consistent state. And if you have a delayed state, like in this case, because the application state in a separate database fed by events is by definition stale. It could be stale by millisecond, could be stale by 10 seconds, could be stale for an hour. And the system is making decision. It's a different level than the user is making decision. The system needs to make decisions having consistent state. And here it's virtually impossible. I even read an article saying in event sourcing, it's impossible to achieve consistency. It's actually rubbish, but nevertheless, I can see where it's coming from. So when you do it this way, it won't ever work. So if events actually used to persist state, this issue doesn't exist. And that's where we come to the essence of event sourcing, is basically using events as source of truth. So if you using events as source of truth, it ensures that you have a strongly consistent system, because then the decision making is taken, the decisions are being taken by looking at the entity or aggregate state, which is reconstructed for event before the command is executed. So it's not some alien store and not another database. It's the same events that you just produced handling previous command. So the entity state in this case exists on demand. So when the command needs to be handled, we load the entity state from the events, reconstruct the state, and make decision on that. So it's not really a state mutation as such. It's the append of event at the end of the stream, and then when we reconstruct it, we replay all the events and get to the current state. There is some hidden power in there. So I gave this example on the webinar that we hosted at Event Store. So for example, this is where I handle the state transitions inside the aggregate where I want to reconstruct the state. So I have a few pieces of state, for example, room ID, guest ID, price, period, paid, stuff like that. And out of the sudden, my booking paid event was not including the amount. And I don't know. I was assuming in my previous version of the model that I don't need the payment needs to cover the full amount of the booking. But then I added some. Sorry.
Good.
So then,
Yes.
oh, is it Greg?
Sorry.
You're talking on the phone, and we can hear you. All right. So
Okay,
in the next version of my aggregate, I decided to do.
Just tell them to put in an extra muffin thing or whatever. It's fine.
Can you mute it? I can try to squeeze muffins to my presentation, but I wouldn't. So in the next version, I decided that I have some extra services put to the booking. So I need to have I might have payments that only cover the partial amount of the booking. And then I introduced the concept of outstanding amount. The point is that this is the same code extended by 2 lines. And when I read the events that I already have, I reconstruct a new state, like a new version of state. And it keeps working because I have all the information I need in the event. The thing is that when you have a state-based persistent and you like project the states to another database and read from there to make decisions, you can never do it. You will have to reproject all the events to get to the current state, to the current version of the state, so to say. So in this case, I've done 2 lines of code, no database migration, nothing at all, and I already have a new version of the state, which is awesome, which is where I think event sourcing shines. So the second pain that I see, and this is the first example that I posted in the Twitter thread, is that people often use event store is like we store events there and then forget about them. And then we use some sort of message queue to distribute events to projections and to external consumers. There is a problem with that. So the most obvious problem that you have 2 pieces of infrastructure, which is the message broker and the event store, and you need to commit 1 transaction to both of them. So you start to use something like distributed transaction coordinator. We just ignore this issue. Most of the time it's ignored and not deal with properly at all. So you can have a chance that, for example, the first thing you do, you store the events to the store. Fine. Then you try to put to the broker and the broker is down and then you fail. And then what happens? Your projections get wrong. They're not stale, they're just inconsistent. Your external consumers are not informed about things that happen. So basically your system is not consistent anymore at all, and it cannot recover. And it's impossible to replay because events in brokers are transient unless you use a persistent broker like Kafka. But here we have message queue, which is a very specific thing. It's not really persistent. It's durable, but like as soon as you consume events from there, where do they go? They disappear, right? So how would you replay? Okay, I want to create one more read model. So I start to replay all my events from the store to the message queue, but then it gets to all of the projections. So how do they know what they need to replay? That is actually not a bit of a problem. That's a big issue, and that's what a lot of people don't realize. Another thing is that you can safely replay projections, but you never can replay to integration components. Because integration components can make decisions of their own. And it might be a cascading reaction, which we had in production once. And some of the people in this meeting remember this. So we replayed the event to the integration message broker, and it all went to hell. We spent a week recovering from this issue, and it was actually pretty fast a week. Otherwise, we'd spend more. So the queues aren't suitable for projections, and the remedy for that is to fit projections directly from event store, and that's where we come to what infrastructure do you need, and that's what probably Greg is going to talk about, to support your event source application in terms of what kind of event store you need to choose. I, of course, advise our database, and nevertheless, one of the things you need to have there is, that's the evil bus, yeah, to be able to subscribe to the store directly. So when you use Event Store DB, for example, in a pending event, you can have subscriptions that can take this event and do whatever they want, and they work in real time. And they will also work retroactively, so you can subscribe to any stream from any moment of time. And because the subscriptions are independent, one subscription can be real time. Another subscription can subscribe from the beginning of times and reproject the whole store. So in this case, you can replay to an existing read model to fix an error. So for example, you just move your checkpoint back in time and then you're kind of good to go. Reproject and fix the issues in your existing read model. The second possibility would be that you create a new read model and feed it from all the events. And that's powerful because then it comes to things like blue-green deployments and A/B testing. So you can create new read models completely from scratch, ignoring whatever you already have. And without influencing any other part of the system, you create your new reporting database. And that can serve completely different purposes. It could be a replacement for already existing reporting database. So you can play around with this. Like for blue-green, you will wait until the new one catches up and shut it down, switching like DNS record to the new API. Alternatively, you can put them all both online at the same time, running in real time, and they will be serving different sets of users. And you can experiment with that, which one is better. And last but not least, message brokers, the classic message brokers like RabbitMQ or like say Azure Service Bus or Google PubSub, previous version at least, they don't guarantee the order. And in projections, most of the time, the order is important. Not always, but in many cases, it does matter. With subscriptions, the processing is linear. So there are drawbacks with that, in particular performance. Nevertheless, with linear ordering, it's much easier to reason about the code in projections and to deal with read models. So another pain, I'm to keep talking about projections and read models because that's a powerful pattern, but you need to handle it with care. So there might be, because when you update your read models in the projection, you do one operation to update the read model itself, and you do another operation to store the checkpoint. If you store it in a transactional database, then it's that's okay, because you can store the checkpoint in the same database and do it in the same transaction. Then it's probably not a big issue, but if you have a subscription, one subscription dealing with multiple projections, and they actually project to different databases, and that might be a requirement, then storing a checkpoint would be a distinct operation. So in this case, you might lose a checkpoint because of this checkpoint store fails for some reason. And then what happens? Then you spin it up again. For example, it restarts. And then you say, okay, I will like reproject last 100 events, maybe last 1,000 events. And then you get duplicate events in the projection. So what happens is that if your projection code has some sort of calculation, so it uses the state of the read model to create new state, so the update operates on both event data and the read model data itself, then it doesn't work. So in this case, I have the booking with outstanding amount $200, and then I project the booking paid event for $200. I get, and on the first run, it does everything properly. On the second run, I get the negative outstanding amount, which should not happen. And you see that's why it's happening, that because I'm just adding to the existing outstanding amount, which I have in the read model. So the remedy for this is basically make projection side important. I know it sounds easier than it actually is in reality, but it can be done. So one of the ways to do it is enrich your events with information that allow you to project it directly without looking at existing information in the read model. For example, in this case, I added the outstanding amounts to the event because it can be calculated in aggregate, and aggregate is always operating on the correct, consistent state because it's reconstructed from events. So what does it give you? It gives you this. So if you project it twice, what happens? Nothing happens, because you use the field and the value from the event to update your read model. You can project as many times as you want, right? So in most of the cases, that's actually enough. So sometimes you can't avoid calculations read model. There are some tricks like using timestamps and versions of the or position on the global stream of the event if you have it. If you don't have it, then it sucks. If you use things like timestamp and ignore previous events that were already projected, because you know when the document was, or the record in database was last updated as a read model, you won't be able to reproject to fix an error. So that kind of sucks. But that only is an issue if your projections are idempotent. Idempotency of projections is the easiest way and the most sort of valuable way to solve this issue, but it can be solved otherwise. So next thing is a read model consistency. That's kind of hard to get because, and I'm not talking about them being stale, right? I mean that they can be stale in relation to each other. So I have an example, and we had this in production not long ago, about a year ago. So we have two different streams. One stream produces telemetry forecast, another stream changes the car state. And the car state can be park, idle, they start moving. So it's actually moving. So what happened is that we had one projection that updates the location of each car. So each car has its record in the reporting database. Another projection updates its state. And because you can imagine that the projection of positions can get pretty hardcore load because it gets positioned like every 5 seconds. It might get stale. While the car state projection actually is never stale because the number of events there is pretty small. So what happens when you look at a map, and the map uses both of them. Sorry. And the map uses both read models on the same screen. Imagine that the state projection is real time. So it says the car has now parked. And you see it as an indicator on the map. But then the projection that projects locations is still working. And because we keep polling it to get new information, the car is still moving. So the pointer is moving on the map, but the car state is parked. So it's very confusing for users. And it's really not something you want to show in terms of user experience. So the remedy for that is like projections can be stale, but they need to be internally consistent. Like they need to support causal consistency. So if they stale, need to be both stale. It's much easier for the user to understand information that is kind of makes sense altogether, rather than have one piece of information that is real time, another piece of information which is stale, if they belong together logically. So the remedy for that is subscribe to the stream that contains both of events from both of the streams and combine projections in groups. So if you have a single subscription that handles both of these projections, it won't happen. So this is how it could have been done. So I have, for example, a car telemetry subscription that updates both the location and car state, but because it gets events one by one, it cannot be inconsistent, as I mentioned before. So it can be stale, but it will be showing consistent information to the user. So, and we talk about causal consistency here, not kind of be in real time, right? And another gain is that you actually would benefit to move from what I call the aggregate state projection fallacy, because that's the first thing we do. So we want to see what it looks like. And because we kind of don't have this way to go to a certain database and see the aggregate state, first thing we do is create a projection that represents basically the aggregate state. It's not ideal because you often don't need it. So you would benefit to have a composite read models that project from aggregation of streams. And that gives you extra power because then your read model can answer a particular use case. And if you have a different use case that maybe have the same data, but it might benefit from using different database technology or using different schema. So you can query it easier. For example, in a webinar, I was building a projection that I had the bookings, but I also built a projection that where a single document in MongoDB was showing guest bookings. So I reverted it. So the ID of this read model was not the booking ID like I would normally have, but it was a guest ID. So I basically turned it around. And it's powerful because then you can fetch all the guest booking by using a guest ID only, and you don't need to query anything anymore. And it's very, very fast. But then the precondition to that, you can have a stream of events that consolidates all the events in the system, at least for your bounded context. So then you can have it, otherwise you can't. And that's the problem with self-built event stores most of the time. So stale read models, that's what a lot of people talk about. And the read model shows information that is not up to date. So in this particular case, for example, when the payment was requested, we have this subscription that projects us to the sort of guest view of the booking, right? But the guest pressed the pay button and the payment has been completed. But because what we show on the screen is that what the green box contains, when they open it again, they see it's unpaid and they try to do it again. They might, at least, right? That's what people usually do. If they see something didn't happen, what they expected to happen, they'll try again. And then you can they start to deal with stuff like double payments and things, which you don't need. You don't really want this. So the usual issue for that is there is no strongly defined SLAs for projections. So it's how stale can they be? And no metrics and alerts that measure this SLA. And that becomes a problem because you basically don't know. Essentially, you are in distributed system world. So part of your components can operate in stale data, but you don't know how stale it is. And without defining SLAs and exposing metrics and putting alerts on top of these metrics, you hardly know what's going on in your system. So there is this concept in distributed system world called lead time. It's basically how long it takes to for the message to come into the sort of queue, and then when it gets consumed and finally processed. So critical time and lead time is that particular time frame. So the lead time extends the SLA, then you have a problem. So you need to have an alert that mitigates this. It doesn't solve the user issue, but at least it informs you that you have an issue. And then you can fix it by optimizing your projection code, maybe making it faster. So you can prevent this from happening. So this is the graphs from production. And the first graph is showing that there was an error. That's the alert we got in Slack saying that this thing went out. So the projection gap, the subscription gap went over to 13,000 events. And in a few minutes, it actually went down. So it was one-time spike. So it's probably wasn't a big issue, but still, if there were users looking at this, they would notice it. So we can react on that. And the second one is basically the lead time. And see the system is stable. There is no alert triggered. So that's why the color, the background color is gray. So everything happens within 3 to 2.5 seconds. And I think that's 95% percentile. So we know that the system works fine because these events are coming from external data source. So 2 seconds is pretty decent because it goes through the mobile internet and stuff like that. For projections, I would expect it to be within 10 milliseconds. Otherwise, it's rather strange. So the metrics needs to be in your APM tool. We have a variety of tools now, like Prometheus, Grafana, APM providers, Datadog, New Relic, applications inside. Just use it, measure things, and expose this kind of metrics because they are very important. Looking at time. Okay, so another pain is, and that's kind of, it's not a big mistake, but it can become a real burden if not being we don't deal with this carefully. So this issue, a picture is coming from the infamous article called "Don't Let Internet Dupe You, Event Sourcing is Hard." The person who wrote it rightfully mentioned this is under pattern. So basically, you couple your domain models of these 3 services with all the external consumers that do whatever they want with it. So basically, when such a situation happened, you got a lockdown of your domain model evolution to all the external consumers. So, and that's the problem, because how can you evolve your domain model if you have countless external consumers and most of them you don't even know about that consume your events in the form as they are, right? You can hardly introduce, remove anything from the event schema because they might use it. You cannot introduce new version of the event because they don't consume it, they consume the old one. And you cannot produce 2 events at the same time because your projection's handling both of them. And so for aggregate state, it's okay, but it will be duplicated. So like you don't want your aggregate stream to contain the same event with different versions. It can work, but it's just a necessary complexity. So my advice would be here is that external public events need to be made explicit. You might not to do it from the start, but it doesn't hurt to put a component in place that actually does what I describe here. So as soon as you have a possibility to put a subscription on the event store, it's real time, right? So then the small component will just do the transformation and publish into the broker. So you don't allow people to subscribe to your event store because they will consume your domain events. And if you do, you probably need to define the special integration stream for that purpose. The transformation bit can be in the very kind of in the first a few months, maybe a year or maybe longer. It can be very straightforward. It just takes an event and as is publishes to the outside world. But it also can filter out some stuff that you consider internal. For example, PII data. You maybe don't want to publish it as it is. Maybe you want to mask it out. Maybe you want to just remove this information from events and publish it forward. Maybe you want to encrypt them. I don't know. But the point is that as soon as the component is in place, which does this transformation, even the transformation is naive, you're on the much safer waters because you can enrich this component further on. And basically, this is your ACL preventing you from corrupting the others and preventing their concerns to corrupt you and decoupling your domain model from external consumers. So basically, I prefer using message brokers to distribute events to external systems, unless we're talking about reporting models, then they actually need domain events. The point there is that these events are transit, they disappear as soon as they're consumed, and the public event is made an explicit citizen or first-class citizen inside your system. So it's important to understand that events, the surface of your event schema form a contract. So it's as important, or probably more important than a command API or your REST API that put in front of it, or whatever messaging API you use for command handling. So these events become a contract. You don't really want to operate with external contracts in your domain model. It's just no go because you lock yourself down. Right. What's going on? Yeah. Okay. Maybe I'm going too fast because I'm reaching to the end of my slide deck. One of the pains that talking to what I have in quite a few production systems, also talking to other people, event store customers, they struggle with having long streams. And that's where this shift happens sometimes, is that people say, I don't want to use streams as a source of truth anymore. I don't want to use events. I would rather use a projection. So long streams come from the fact that it's actually not the correct diagram. So sorry about this. So long streams take too long to read. So imagine that if stream grows beyond 1,000 events, I know what Greg was usually saying, that doesn't matter, it takes a second to read. But if you have a heavy load on your system, 1 second multiplied by 1,000 command per second, it takes quite a while, and it loads your store as well. So read operations are not for free. They're easier than writes, but they're not for free. So there are quite a lot of concerns about internals of different event stores. Nevertheless, it needs to reach out to all the events, scatter it around a huge database potentially, and fetch them all in random fashion, compose them together, and give it to you. So long streams can become a problem at some point. I see that there are a couple of things there which can provide a remedy. So first of all, for me, usually if I see the evolution of the business object, it rarely exceeds like 100 events, maybe more, but not much. So below 1,000 events, normally it's really a little number. So the question is, why long events come to life? Well, long streams. So what is the problem? Most of the time, in 80% of cases, probably more, it's about wrong boundaries. So the aggregate boundary is too big. I understand the concerns, so we try to make things safe. So we encapsulate as much as we can to keep the transaction boundary strong and keep the invariance inside. But sometimes we mess around with cross-aggregate invariants and try to make them aggregate invariants. So we make too big aggregates. When the aggregate is too big, of course, it gets too many events. So think about the product in the e-commerce system, and especially the product stock. So every batch you receive and every sale you complete changes the stock, and you have this thing going up and down all the time. That's probably a bad example of wrong boundaries. Maybe that's a correct decision to do it this way, but there is a remedy for that too. But sometimes things like trips per car accumulated in a single car aggregate. That's not right, because the number of trips per year might exceed thousands by far. It can be like tens of thousands. And what do? And every trip has its own event. So then you think, okay, the trip needs to be an aggregate on its own. So when I drive, it creates a new entity and puts it in the store with all the events. Then you start shifting invariants that you consider inside of the aggregate, so car trips or whatever you call it, to cross-aggregate invariants. And they're actually not that strict, because some things can only happen naturally. For example, if the car has driven the trip, it cannot happen again. So it must be technical or stuff like that. So sometimes these cross-aggregate boundaries can be served by read models if they're not stale for a very long time. So it is manageable. It is possible to make small aggregates, and that's what people should do. Not too small, like not one command per aggregate and stuff like that, but reasonable. Use your language, use your imagination, whatever modeling skills to make it proper. Snapshotting is widely used as well, because that's a very technical solution though, and the problem might be not in tech, the problem might be in boundaries, but you can still solve it by doing snapshot. Snapshot is basically take the aggregate state as we know it now in the domain model and put it in another stream. The problem with that is the snapshots needs to be version 2, and sometimes, like I showed you, by changing 2 lines of code, I got a new aggregate state from event information. With snapshot, it won't be possible, because the snapshot contains what it contains, it cannot change. So if I would have a need to upgrade my aggregate state, I would need to kill all the snapshots, or at least one that is the last one. Or I would need to kill them all and basically replay all the events, get a new snapshot, and put it in the system. It might take time, it might take too much time. So that's kind of also not ideal, but it's a quick remedy. So it's like if your system struggles with performance, you can actually do it. But then you might reconsider your boundaries. And closing the book is an interesting pattern. In Greg's event versioning book, it's called bankruptcy. So when the logical period comes, I think I have a demonstration here. When the logical period closes, so there is some point in time, and in many businesses it works like this, like in accounting, in banking, and a lot of finance domains, but not only that, but not only in finance. For example, that product warehouse management, whatever inventory level stock, can be done the same way. So for example, in stock management, the logical point when you can close the books, and I will tell you what it is when they actually count the physical presence of product on the shelf in the warehouse. And as I learned from one of our customers, they do it continuously. So just separate warehouse in zones and then go around and count the single product. When they do it, they can actually tell the system, I know for a fact that I have 100. And the system actually gains from it, so there where the gains come, because the system can understand if the stock level that it knows about matches what's there in reality. And then the system can reconcile it and produce some interesting information. For example, some items disappeared, they were stolen, and some items actually are present there, which they shouldn't. So then they can decide what to do. How did it happen? So you can have some analytics. If your stream is not doing that, and if the counting is not kind of implemented as closing books, this will never happen, because you kind of never know how to reconcile reality with ongoing stock changes, because it goes up and down all the time. So in this particular case, I was mentoring a person, and then we went to this scenario: how do we deal with account aggregates in the bank when the account is like long living thing, and we know that things like encapsulation of all the transaction, the account, all the transaction itself is a separate aggregate, But to know the current balance, we cannot rely on the read model, so we need to have some representation inside the account. And we created this account aggregate. And she said, like, it will be millions of events long by the 10 years. So you're right, but the period where you look at a bank, and that's where it's very always useful to look at how a real life system work. We look at the internet bank and we see that all the transactions are there per month. So what we thought we were doing is basically when the 10 comes, reconcile the account with a special event, and this reconciliation account will look like a snapshot, but it actually closes the previous period, which cannot be reopened, and we move forward from that. So it doesn't lock our event schema to anything, because we know that the snapshotting happens or reconciliation happens in a fixed period of time. So when the next period starts, we can have a new version of the state, we can introduce some new events and stuff like that. It actually works pretty well. And the nice thing about it that we brought up the first class domain concept, which we didn't have in the model before, and implemented it naturally in the domain model. So we didn't invent anything like technical snapshotting, but implemented what's important for the business, the concept that hasn't been there before. So for long streams, there might be something that you can look and find the business concept that corresponds with closing the book pattern in that particular subdomain and implement it to help you managing the stream length. And this particular stream, it can be archived after reconciliation. Like you can decide, I want to archive after 5 months. So you can just truncate a stream. And then it will be always roughly the same size. And you never need to read all of it. You can read from the end of it until the first reconciliation event, and you know what the current state is. So you can be really creative about it, how to do it. So last but not least, and this is the right diagram, which is not a diagram at all, is the probably one of the biggest pain is the event schema evolution. So I wouldn't talk about it because it deserves, like, there is a talk published by Greg or delivered by Greg a long time ago. It's Greg's book out there, so that's what I mentioned. Read the Greg's book. Where it comes to event schema evolution, there are a variety of techniques. There are a lot of techniques that can help you to move from one schema to another schema. So in the most cases, like maybe in half of the cases, you don't even need to do anything because you just need to add one more property to events, and that's fine. So the only thing you might need to be doing is basically to change this integration transformer that publishes public events and maybe introduce a new version there. I usually version all my events from the start because it doesn't cost me anything. So I just write v1 and like define a namespace with v1 and then call it a day. And all my events are v1 until I find the stable model, or at least until I put stuff in production. But sometimes you cannot avoid migrating the store. Like one of the patterns that Greg promoted before, or I don't know what his opinion now about it. The store can be copied from, like, you can copy all the data from one store to another. And when I start looking at it, it's actually pretty powerful. So imagine this. You decided to drastically change the schema, and drastic changes of schema can involve splitting one aggregate into two. So they split to two different streams. You can, for example, decide to remove some PII from your events and put this PII to separate streams so you can deal with GDPR easier, right? Or you can do encryption, stuff like that. But you need something that will just take your store and migrate it. And we were always thinking like, yeah, that's one time. So we need to shut down, migrate the store, and spin up the whole system with a new store. How's this is going to work? And then what we figured out lately is that, at least for me, it was kind of, I know that's for some people obvious, not for me, I'm slow. So what could be done is basically you set up a component that subscribes to all events from the original store and writes events to the new store, right? It's like a normal subscription, like a projection, but it doesn't project to read model, it projects to a new store, and it projects everything in keeping the order in place. And the thing is that then you can do everything you bloody want. You can split, you can transform, you can delete some stuff. You can even query external database to populate information you were previously missing in your events. It's totally possible. And you can run it side by side for quite a while. And you can analyze the content of your new store and see if it actually suits your needs. If you're not happy, you kill it and you start doing it again. So of course, it works up to the certain point. So it doesn't work for terabyte size or petabyte size of stores because it takes time to do it. And if you want to keep the global order, it must do it one by one. So take one event, project, and stuff like that. There are ways to speed it up, but nevertheless. And then you get the physical limitations of a target store, how long the operation to write one event takes, right? And you cannot overcome this, it's just physics. But in most of the scenarios, it's actually possible. And then you can even split stuff to two stores. Like say, I have one gigantic store that served two bound contacts, and I decided to split it into two bound contacts. So you can split into different stores to keep stores isolated. It's all actually possible. And then you can start shifting certain components to the new store when you're happy. And the first thing you shift is basically projections. So you create new projections using new event schema, and you put them in production using that store. And because the replication gap when it comes real time is very small, then it's not a problem at all. You can feed your APIs and stuff with projections that work on the new store. And when you're happy with everything, then you can start switching command handlers to that new store with new versions. And basically, you strangle the old store to death, and then eventually it will shut down and doesn't need to exist anymore. So it's actually not as hard as I previously thought. And it's very powerful in terms of you can even run some experiments on the other side, right? Because it's completely detached. It has nothing to do with your operational store at the moment. It will become operational store eventually or not. But then you can use it to run some experiments and see how it actually works. You can also use it as a backup, but that's a different story. So this one is pretty big. So Greg wrote a book. I wish some images would be better. Nevertheless, it's very interesting, and maybe it needs to be like you need to spend time reading and trying things out, because all the patterns that I mentioned concerning schema evolution and closing book snapshotting, store migration, things like that are there. And there are more advanced patterns about inline migrations and things like that. So that's pretty interesting. All right. So to summarize, use a proper store. Don't use infrastructure with persistent topics as event store. It will never work. Use your events as a source of truth to reconstruct your aggregates because it gives you consistency. Don't pay too much attention on stale projections because they might be okay, but do pay attention to how stale they are and measure the gap. I wanted to make this talk like call it mind the gap with a little bit more demos, but that's a different version, right? Mind the gap. Well, when you're mining the gap, measure the SLAs according to predefined, like written down contracts. So you need to know where to pay attention, where not to, because some projections can be stale for days and nobody will ever notice. Don't spend time on optimizing those, right? Optimize what you actually need to optimize. And use your APM systems. What I haven't mentioned is basic distributed tracing. It's a topic on its own again. Putting traces on event sourcing is extremely interesting. You get a lot of new insights when you look at it for the first time. You probably never knew how the system works before that. Schema evolution is not as hardcore as some people think. So try out some different patterns, and maybe I personally or the event store will give you some tooling to do that in the future. We are discussing that. So long streams can be indication of wrong boundaries, so look at that first before applying any tactical patterns to mitigate this. And please do not use event buses or message brokers or whatever kinds, especially those that are like RabbitMQ, PubSub, to feed your read models. Please don't. But do use them for integration events and consider promoting your integration events to the first-class citizens. So you decouple your domain model, so you get freedom in your domain model evolution and keeping your contract stable at the same time. And that concludes my talk. Questions?
Great. We have actually 3 questions in the chat. I don't know if you can see the chat.
Yes, I can see the chat.
Yes.
So what strategies do you use for group update types of commands in your in event source systems? Yeah, I don't. Yes, I understand. So basically, when the command seems to cross the boundaries of a single aggregator entity, whatever transaction boundary, I actually don't. What I do is the command like this could exist, commands like this, but I use it in a way that I split it up. So first of all, I would query whatever I need to do in terms of individual operations, because my rule of thumb is one command, one transaction. So this kind of command don't work this way, because you might start doing it in the loop, and then eventually it breaks in the middle, and then you retry the command and start doing it again. So if your database is slow, you get to like about the players. So first 1,000 of players, before the database gets suffocated, you add them 100% bonus at the time after 5 retries. So it's probably not something you want to do, but you can easily split out the command, because message brokers, for example, are much more reliable pieces of infrastructure than databases, especially when it comes to performance. So I'm sure it's interesting modeling questions, because again, people might say, but what is your guarantee that you emit as many commands as you want and not less, because you might retry that too. I guess there is a good topic for discussion. I haven't thought about it. You usually split out and fan out a bunch of commands. It's not a problem, but if you need to have strong consistency guarantees, I would store it somewhere still. So like, for example, if I have this like put through, I would have some place where I track who actually received it, right? So next time, if the command gets retried and I need to split it out again, I will check that small store to understand to whom I sent it already. So if it makes sense. So event stories for the main events, and should not mix events from different band contexts. Is that the projection we want? Yes. Excellent question from Mateusz. Actually, that's exactly what you want to do. You might want to project from multiple bound contexts. You definitely want to project multiple aggregates. So here we come to the idea of transactional database versus reporting databases. We know that the read models are effectively our reporting databases, but you might have a reporting need that covers multiple bound contexts. So that's not uncommon. That's actually pretty common. So it boils down to what you can find it in Eric's books, this in strategic design, a chapter about relationship between bound context. And when you have an isolated system that produces integration events, pushes it out through the broker, you're basically operating with like customer supplier, maybe partnership, stuff like that. Well, not really, no. You operate in a relationship model, ideally, which is published language open host. So you say, this is my API, off you go. Don't bother me, right? So when it comes to this particular case, you need to understand that the reporting model becomes like when it cuts the bound context and it aggregates from many places. It comes to business analytics, it comes to the big reporting engine and stuff like that. It becomes a context on its own, right? It's not something that doesn't have any logic, right? It's not just a projection logic sometimes. It may be a pretty complex piece of software. So promote it to the bound context and accept the fact that you coupled. There is no way around it. So this context will work in a partnership relationship with anyone else who they consume events from. So you could put broker like persistent broker like Kafka in between them, so you can still operate on integration events and support the schema in terms of stability. So that might remedy the issue, but sometimes you cannot avoid them from subscribing to your store and projecting to it. So just embrace this fact. If you can, you can try to isolate from them. If you can't, just deal with this. So this is powerful pattern to produce read models across bound contexts, but it needs to be handled with care. So closing the books remedy. Yeah, I think I don't know, Piotr, what they mean by huge amount of streams. Huge amount of streams is actually not a problem. Maybe you can explain why is it a problem for you to have a lot of streams?
Either you can write or
oh, it takes space.
Okay.
Okay, yeah. I mean, yes, you can. It's more like I think Eve, are you there? So what you were talking about, closing the books is one thing, and as I said, like when you let's look at the slide now. So share again. So right here, what happened is that we do have, let me make it, yeah, it's okay. So we have two physical periods, time periods, which represent a month, right? And we know that after 6 months, we don't really care about historical events anymore because we know they are like fixed in stone. They cannot be removed, they cannot be amended, and we don't actually need them for any purpose except of showing information on the screen for the user, which is fed by the read model anyway, and the read model becomes, after 6 months, a PDF file stored somewhere in the cloud blob. So what we do in this case is basically we can truncate a stream at that point. So here is coming the point of truncation. So this truncation point can be actually in 6 months time. It can be also here after a single month when we reconcile the count. And if there is no movement, well, you truncate the stream and then all events disappear. And if the count is stale, you will only have the single events coming every time, because you still, in some businesses like in banking, you still need to produce a statement, right? And the bank statement can be empty. Opening account 100, closing balance, opening balance 100, closing balance 100, that's it. But it still needs to be produced because that's a good document that needs to, for reporting, that you need for reporting. But then you can first decrease the number of events you have on a stream. That's one thing, it's big streams. And some streams that can be archived, basically. Archiving is very valuable. You can say, I don't need this anymore, right? So I introduce something in my aggregate store that will be able to, or the archiving is actually not for the store to decide. You might just decide to do it in a different component, but the store might get this functionality that it looks to the archiving place if it doesn't find an aggregate, but it knows that it needs to be there, and then basically unpack it. It's like you pack it, put it somewhere else, and because there is no movement, no events, you don't need to project anything, stuff like that. And when you need it, you can unpack it. At some point, like you have a customer who left you and you don't deal with them anymore, you can just compact them and move them out entirely, because you know there are no operations on them anymore that's gonna happen. Unless you want to keep the, like, you were a customer of mine, I don't follow GDPR rules, so I don't delete your data. So when you come again in 2 years' time, I will unpack you. So there are different scenarios. You can delete streams if you want to save space, because like you don't need them anymore, right? So, but again, I don't prefer not to keep data in the system that I don't need, because I might get easily in GDPR violation, especially when it comes to user data. So I'd rather anonymize, move it out, or just kill it. So I hope it makes sense. All right.
Yes, great.
So regarding from Andreas Grimm, regarding the transformation transactions you were mentioning, translations, yeah. Knowing about different context to context relationship types. Oh yeah, it's not a question. Yeah, thank you. So yeah, if you're right, it could be driven by regulations. And I think that's the first place where we need to look when it comes to closing books and archiving. First place to look is actually the business. That's why I'm kind of against snapshotting as a technical pattern. I'm not really against it, I use it. Still, it's like a second choice, or third even. So first look at the business. Maybe there's closing books already in the business, you just don't know about it. The only thing you would need to do is to embrace this domain concept and put it in your software, which is beneficial anyway. So there could be regulation that force you to delete the data or close books and reconcile things, and just do it. And that saves you your buttocks at some point. So just be aware. And And Andreas is writing, regarding what if projection, we want to project events from a different context, the following could help. Yeah, have a translator for every context you consume events from, and then translate to your own model language and use as your own domain model events and store. Yes. So basically, this is sort of advanced replication mechanism. So you consume events, public events that are published by one context, transform it to your own events, because basically events are facts, right? So you cannot change it. When you react to events, you do things according to your rules. And you might say this shouldn't happen, and you can the only thing you could do is raise an alert about it. But you couldn't say it didn't happen or pretend it didn't happen. It can happen. This situation is possible in deal with external systems that send you rubbish data. But again, then you need to react accordingly in terms of telling them that they send you rubbish data, not just ignore it entirely. And this can work in the reporting models as well. So Oscar posted the link to and Rasmus both posted the link to Greg's book. Yeah, great.
Yeah. Okay.
So this is it, I guess. People just chatting, no questions.
Yeah,
and
really great talk, really interesting. Thank you. If you'd like to stay around, Alexey, you can do that, or
I will. Yes, I will.
Yeah, that's good. So if Greg is ready to go, the stage is all yours. He's having his muffin, probably. Yeah. Now we can hear you.
You guys hear me?
Yeah, we can hear you.
Great. Let me just figure out how to share my screen here.
Yeah. Was the muffin good?
It was mediocre. It was Dunkin' Donuts.
Okay. Okay. All right. If you're ready to go, Greg, just take it away. Thank you.
Do you guys see my slides okay? I know sometimes the slides like show up outside, or
we can see them. It's all good.
Okay, great. So what we're going to be talking about for the next bit is not so much about event sourcing, but about how to actually build an event store. And what we're going to be looking at is how event store itself actually works. This is something that isn't really talked about very often, but there are quite a few interesting patterns that actually get used inside of event store. And there's quite a few attributes about event store that a lot of people don't realize even exist. So let's start out with who am I? I'm guessing most people here have probably heard of me at some point before. I have worked much with event sourcing. I have taught classes all around the world about event sourcing. I was the lead architect of Event Store. In fact, much of the code that we're going to be discussing today, I actually wrote myself, at least in the first version. So, what is Event Store? Well, Event Store is a kind of hybrid between a queue and a database. Basically, you can put your events into streams. You can then read events out of streams. One thing that's very important to note with Event Store is that these streams are intended to be very, very finely grained. It is intended that you will have one stream per order in your system, or one stream per aggregate instance. For us to have 500 million streams is absolutely no problem. This varies greatly from a lot of other pieces of technology that are out there, where things are looked at more as queues, and then they have things like topics inside of queues. We kind of have that relationship flipped upside down, where we have very, very fine-grained cues, and then we have aggregations of cues, if that kind of makes sense to people. But what we're going to be getting into in this talk is really dropping low level into Event Store and how Event Store actually works. So internally, from an Event Store perspective, Event Store is a log. You append things to it. They are written down to the thing known as a transaction file. It is logging the events that you are doing as you are doing them. This is a very well-known pattern. If we were to go look at SQL Server, we could talk about a transaction log. A huge number of databases actually work this way, where they have a transaction log that is appending transactions. And then they have indexes that come back into this, and they might even have where you are taking stuff out of the transaction log and putting it off to other places. Now, with Event Store in particular, it's not really worth taking the things out of the log and putting them in other places in many circumstances. The reason for this is, one, you can index back into the log, and two, a lot of people who want to be able to use an Event Store are looking for an ability to get something that would be quite difficult there, which is to read from all. So I want to get all my events in the order that they were written. If I'm pushing this out over into other storage mechanisms, while I may get faster stream reads, I would lose my ability to actually really be able to do an all. So internally, it works as a log. And again, this is a very common pattern. And if you look at most databases that are out there, you will find that they operate in the same way with a transaction log. So let's take a look at how our log actually works. So here we have 1, 2, 3, and 4. These are just transactions that have been written into our log. When you go to write 5, we are just going to append that to the end of the log. Again, this is a very, very common way of structuring a system. It is append only. Everything that you do shows up at the end of this log as a new transaction. It does not matter whether this is a write, whether this is a delete, whether this is, if we had updates, if this were an update, it still comes to the end of that log. Conceptually, everything inside of Event Store follows this model. It is structured as an appending log. Now, this log that we have in reality, if you actually start getting into the code, it's not just one big appending file. Making one big appending file would run into a lot of problems over time. Instead, this giant file gets broken up into pieces, which we call chunks. If people are actually looking for the code involved with this, this would be in TF chunk or transaction file chunk. All that we're doing with a chunk is saying that instead of having one giant thing, we have pieces of things that make up that giant thing. We can look here. So here I have chunk 1 and I have chunk 2. These are very, very small chunks. They only have 5 events each in them. Conceptually, this is events 1 through 10. All that I've done is group them in terms of how I'm going to put them down onto storage. In my first chunk, I have 1, 2, 3, 4, 5. In my second chunk, I have 6, 7, 8, 9, 10. But conceptually, this makes up one log. Now, if we were talking about a really big database, you might even have 5,000 chunks. Let's see, 5,000 chunks would put you at about 1.2 terabytes by default. So I'm pretty sure we actually have people that are doing that. In fact, I can even probably name the customers doing it. But all of the chunks are doing is just making small incremental bits as opposed to having one giant thing. Because one giant thing would be really, really difficult to manage. And we're going to find out a few other interesting bits about chunks as we get a little bit further into the talk. One thing to consider when looking at things like chunks. Chunks are very, very file system cache friendly. They're file system cache friendly because they are never changed. And I shouldn't say they're never changed. They're only changed in large batch operations, which actually create a new file, and we're going to get into that in a few minutes. They are immutable on disk. And nearly every file system that you will find is quite good at dealing with immutable files on disk. This is literally a best case for most file system caches. One question I get a lot, though, is since you're writing to these appending files, what happens when you get things like power outages? I'm not sure if people knew this or not, but Event Store actually offers a strong durability guarantee. Providing you are running on hardware that is actually durable, Event Store will give you a strong assurance that your data is actually durable. And when we say a strong assurance, it does not mean that we've looked at the code and we believe that this should probably work. It means we've literally taken hardware and run it for years doing power pull testing on it and ensuring that no data was lost. I think those are currently down now. I don't think they're still up on the website. But you used to be able to go to the website and you used to actually be able to pull up the status of the power pull cluster and watch it actually doing the power pulls. It was pretty cool. It was all automated. Did you know that you can actually go and buy a little device that you can send an HTTP request to change power on something? I was amazed when we were able to find that. So when we're dealing with things like power outages and ensuring durability, the main thing that really comes into it is checkpointing. So as we're writing, we would write event number 1, then we write event number 2, then we write event number 3. When I flush to disk to make these things durable, I will update my checkpoint at the same time. And my checkpoint will point to where in the log have things actually been flushed to. So in this case, my checkpoint is at 3. This means 4 has been written, but it's not necessarily known to be durable yet. In other words, I cannot respond to event number 4 saying this thing has been written. I need to wait for that checkpoint to come forward before I'm able to respond for it. Our checkpoints represent the last known good place in the log. There can be other things that are there in the log afterwards, but that stuff isn't real. If I were to have some catastrophic situation, I only know that I'm good up until that checkpoint location. And again, that checkpoint location is just the position inside of my log where I currently know that I have flushed that down to disk count. And remember, I've mentioned it already, but you never actually know that something's been flushed to disk, and there's some hardware that you might run into problems with, things along those lines, because it lies. But conceptually, that's how everything works. When we restart, we will start from that checkpoint and come forward. It's a really, really simple process if you stop and think about it. What we're doing here is we're linearizing everything, and then we just remember where we were inside of that linearization. This pattern gets used all over the place when you start getting into things like databases. This is the concept of a transaction log in your SQL database. This is the concept of a transaction log that's linearizing things and then running essentially single-threaded with assured ordering. All I need to do is I need to mark the position that I know that I'm last good at. And therefore, I can just come up from that position and continue. Note, because I can continue a second time, this also means that everything that I'm doing must be idempotent, because I might end up doing it multiple times on, let's say, a crash. And it's very, very important to note, with event store in particular, that your write will never be acknowledged until the checkpoint comes ahead of it. It will always wait until that checkpoint has come forward. And this is very important because this is part of what assures that your write will never be lost. If a checkpoint were behind where your write is, then that write doesn't really exist yet. There are cases where you might actually have to truncate to that checkpoint. Ensuring that the checkpoint is ahead is the core bit that assures the durability of the system, if that kind of makes sense to people. We have to think about it as this appending log, and that my checkpoint in the log is ahead of where I am currently writing. So long as that is true, we will not lose anything. And I cannot stress enough that we do not know if your data is actually on that disk until we've hit a checkpoint. There are cases where on a failure and a restart, we might truncate back to checkpoint. I cannot respond to your write until the checkpoint is ahead of your write. And again, this is all assuming working disks here. There are many disks that do things like lie to you. And when you start getting into those, there's not much that you can do about things. When I tell the disk, I want this actually put on disk, and it says, yes, sir, I did it. But it really didn't. There's only so much I can really do. Now, all that we've really gone through at this point is saying that event store is log structured. And this is absolutely true. Event store is primarily log structured. The main storage of event store is these chunks of the log, and things get written directly into that log. They are not put out on the sides or, and again, this is also going to be true for many of your SQL databases, your key value stores. It's a very, very common pattern. But just having RTF chunks isn't actually very useful unless the only thing you want to do from them is read from all. If all you want to do is write events and you want to read from all, it would be a perfect model for it. However, most people don't want to read from all of the time. They want to be able to read from streams. So the question becomes, how do I then index that giant log into millions of smaller logs so that you can do fast reads of the smaller logs? And the way that we do that is actually through indexing. In Event Store, there are actually two distinct types of indexes. If you want to go look inside the source code, one of them is named mem table, and the other is p table or persistent table. Mem tables only live in memory, and they live for a short period of time. P tables are persistent on disk, and they last forever, essentially. As we come through the log, we start building up a mem table. Mem table, again, is just our in-memory index. All that we are doing is taking those events from that log and indexing them into our mem table. When you go to do a query, we hit the mem table first. And there are no p tables for me to go look at as well, I just return you the events out of the mem table. An easy way of implementing a mem table is we could use a dictionary of string, and then basically you're just going to have pointers back to where the events actually live. Basically, I've got my stream name, and then I've got pointers back into the log saying where those things actually are. By default, your mem table is going to hold 1 million items. I don't know it off the top of my head. I can go pull up the command line option for it. There is a command line option that you can make your mem tables bigger. 1 million items seem to be a reasonable default for a lot of systems. If you are running, let's say, a 1 terabyte database, I would suggest making your mem tables significantly larger than 1 million items. But when you're just pulling out Event Store and giving it a go, 1 million is fine. You probably won't ever change it. Now, as we're coming through the log, we've got our first event here, and then we've got ... Of course, there's a lot more dots than that as we're going up to 1 million. I would have drawn all the boxes, but it would have taken me hours. They're coming up into my mem table. And again, this is just my dictionary of string of references back to the events that I can look it up by. Once I hit 1 million events though, and again, this is by default, I am going to create a new mem table. And I will continue following the log. All the new stuff is going to go into the new mem table. And the mem table that I was working with previously is going to be converted into a p table, which is a disk-based index. Basically, I'm just saying, here is my existing mem table. Create a p table out of it for me. When you're done creating the p table, you can free up all this memory. So let's get into what a p table actually is. P-tables are persistent sorted arrays. Basically what we're doing is we are writing for every record that was in the mem table, which included the stream name and the position of those events. We are then putting that into fixed width records into a P-table. And as we do that, we sort them. So P-tables are always sorted by their key. Their key is hashes of the stream name. This makes it very nice because they are fixed width. We could binary search that, couldn't we? If I know that every record is 128 bytes, and I know how many records I have, I can binary search this big old file of these records. This is precisely what P-tables do. There's also caching of P-tables. When you go to control the caching of P-tables, you control it by the depth of the caching. When you think about P-tables as being sorted arrays and we're binary searching them, that depth is actually referring to the depth of the tree. How many levels on the tree do you want to cache? Again, this is a very, very simple model. And it's one that most developers should be able to understand relatively easily, algorithmically. If you want to get into the source code for P-tables is all up online. You can jump right into it. But over time, we don't just want to keep creating P-tables. Let's say that you decided that you wanted 10 million records for every P-table. And now you did 100 million writes. So now you have 10 P-tables. Well, that would mean that I'm going to need to do 10 P-table searches for anything that you're trying to look up. I'm going to need to hit table 0, then hit table 1, then hit table 2, then hit table 3, then hit table 4, then hit table 5. Think about how many comparisons I'm going to have to make searching 8 1 million item P-tables versus searching 1 8 million item P-table. I'm going to need to do a lot more comparisons across the small P-tables than across the larger one. So what we start getting into is merging of P-tables. So let's say that I had P-table number 1 with 1 million records. Then I have P-table number 2 with 2 million records. Now I'm going to merge them. And we're going to take those 2 P-tables with 1 million records each, and we're going to convert them into 1 P-table with 2 million records. Remember, these P-tables are sorted. So essentially, all I'm really doing is going through 2 sorted files, creating a 3rd sorted file. I'm pretty sure we've all done that type of sort before. It's basically just read straight down. You're just looking at the record from each one, which one is bigger. You pick that one as the next record. It's a really, really, really simple process. But once I have that new one of 2 million, I could then remove the 2 P-tables that were 1 million each. And my searching is going to actually get faster because now I'm doing the 1 search across 2 million records as opposed to 2 searches across 1 million records each. We might even then have file 3, which is 1 million, and file 4, which is 1 million, which then I merge to the 2nd level, another 2 million. Now, when I do that, we're going to go look at this level And we're going to see that we now have two files of 2 million. So we're going to take those, we're going to combine them, and we're going to make one file of 4 million. Basically, what we're doing here is we're just constantly trying to recombine at levels, trying to make bigger files. Every time a bigger file is made, we can remove things and our searches will get faster. There's also the ability to force this to occur, but most people wouldn't be doing that by their choice. For most people, just allowing the automatic merging to occur is going to be good enough. And it will constantly keep pushing you to bigger and bigger and bigger files in order to help optimize the number of comparisons that need to be made. During this merging process, I can also come back and check if the items that are in that index actually still exist. If they do not exist, I can remove them from the index that's actually being generated out, the new one. Once I've then deleted the old index, that item is now gone from the index. And keep in mind, everything that's being done here is being done in a purely immutable way. This also applies to deletes. As we go through and we actually start deleting things, let's just delete events 1 and 2 here. Now, when I deleted the events 1 and 2 here, this could be with a max age, this could be with a max count, this could be a truncate before. There's lots of different ways I could have ended up deleting these events. But we now see that 1 and 2 are deleted. When we go through and we run, when I generate out the new file, we're just not going to include them. So when I have still the old file, I look at my index, and my index tells me that those things no longer exist. So when you try to read them, I tell you that they don't exist, but they're still on the disk because the file is immutable. Once we run the scavenge, then we will physically remove those things. Another common thing that we run into is when you're doing lots of deletes, your chunks start to get small. You can imagine you were deleting a whole bunch of data from 2 years ago, and now your chunks from 2 years ago, as they're being scavenged, instead of being like 255 megabytes each, now they're 20 megabytes each. So part of this process is that we can actually go and we can take 10 TF chunks. As we scavenge them, we put them together into 1 TF chunk, which represents the 10 original TF chunks. This helps us in a lot of situations dealing with things like file caches and just having the number of files exploding over time. Being able to merge multiple TF files into a single one is actually very, very useful. Now, just some quick things before we head out. Event Store supports full CRUD style operations. And yes, I know there's no update there. I guess there kind of sort of is if you squint at it in just the right way. But all of that is done with the entire data model being append only, it's additive only, and it is immutable. All your data on disk is fully immutable, even though we support all of this kind of stuff. You can, in fact, run Event Store on immutable storage, which we're going to talk about in just a second. only mutable things that are actually on that disk are the checkpoints. You have a reader checkpoint, or sorry, a tracer checkpoint, you have writer checkpoint. These checkpoints are only 8 bytes each. All they hold inside of them is a long that's pointing to where that checkpoint position is inside of that log. Literally, there is nothing else associated. It's just a log and these checkpoints. Everything here could in fact run on a worm drive if we were able to give 24 bytes of mutable storage. So if I could use, let's say, a little tiny flash disk that had 1 kilobyte of storage on it, that I could put my checkpoints on, and then I had 1 terabyte of actual data, I could run that 1 terabyte bunch of data on a worm drive to show that it's never actually been deleted or manipulated. The only thing that I would need to put outside is the 24 bytes of my checkpoints. Immutability is wonderful. When you think about database systems, especially when they're supporting mutability, they can get horrifically complicated. Event Store runs a dead simple model. And the entire simplicity of the model is based on the immutability of the model. Remember, there's only 24 bytes of mutable storage. Everything else that we do is done in a purely immutable way. This is where a lot of the simplicity of the system comes from. This is where a lot of the reliability of the system comes from. Dealing with mutable data is really, really hard. Dealing with immutable data is very easy. This is why Event Store actually focuses on immutable data. And with that, if anyone has any questions, and I'm guessing I have to pop over to the thing to see the questions.
Yes, there are 3 questions in the chat. Can you see the chat?
That's what I'm trying to figure out how to do.
Or do you want me to read the questions?
I know what I have to do.
I can. Do you read them, or shall I read them?
I'm just scrolling to the right spot.
Yeah. Okay. It's about checkpoints.
If the checkpoint is not ahead, then the append has not been apt to the caller. That's why you might truncate things after the checkpoint, since it has not been apt. Correct. You cannot have something that is ahead of a checkpoint that has been acknowledged. It is impossible. Because it's not considered to be written until the checkpoint is also written. So anything that's ahead of my checkpoint is nothing. There's no chance that I've ever told anybody anything about it. Next question. Mem table can be persisted as is because the chunks are immutable. So mem tables are not persisted as is. All right, they're converted to p tables. You can always persist the mem table as a p table because everything is immutable and append only. I never need to change something out of a mem table when I convert it to a p table. If there were any more transactions that have come in further along in the log, they're going into a new mem table right now. And when we look things up, we go to the mem table first before we go to hit the p tables. So for instance, if you wanted to know what is the latest event in stream foo, I'm always going to check my mem table first before I go hit the p tables for that. If that kind of makes sense. And we got another question here. P table merging. Is there a limit to how big they can become? No. I have seen them be many, many gigabytes. They will continue doubling in size, growing in size, as that process occurs. Now, once you start getting into very, very large databases, you will start to see some performance degradation over that. And when I'm talking very large databases, I'm talking terabytes. And there will be some things that you need to tweak, like for instance, what the caching level is. If you remember, we talked about how it's actually a tree and how many branches down the tree do you want to cache? This is one of those things that you would probably need to be configuring once you start getting into things like terabyte-sized databases. Any other questions?
Not in the chat. Not from me. Yeah. If is active. That's good. Any other questions from any other listeners? If not, I must say it has been really, really great listening to you guys. Thank you very much for taking the time to prepare this and do this. And Greg, such an early morning for you. You got the whole day in front of you, so just try to make the best of it. And
lots of time to sleep.
Yeah, exactly. And Alexey, very good. I'm very thankful for you spending the time. Andreas, do you have any further questions?
Not really. I just concur with everything you said. Thank you very much, both Alexey and Greg, and all of the audience.
Yeah. So please check in on the Swenug sites and please check in on Infozone sites as well. And take care, and we'll see each other another time.